Thank you guys for turning up to this session on InterSystems Kubernetes Operator. I'm Luca. I work for InterSystems as a product manager, and today I will be assisted by Steven Lubars, software developers that is gonna go into the details of the operator. So the agenda is just going to be very much, why Kubernetes. I think some of you were already at the previous session, so it will be very quick. Kubernetes Components, what is an operator, why do we need it, and then we're going to take a quick look at our own operator. So the what and why is, once upon a time there was a container, it was cool, and it was on my PC, and it was great. And then when I invented to create another container, web server, maybe some dependency of my application, and I wanted to test as a developer, I used Docker Compose, and that's a great tool that I invented. The problem comes, of course, when we go to the cloud, right? Or to your on-prem data center. You open a cabinet, you go 25 physical servers there. How do I make sure that these containers can talk to each other? And how can I make sure they are administered and managed? And so Kubernetes is just an open source container orchestrator. It's a platform that allows me to automate the deployment, the scaling, and the management of containers workload. So let's go have a look at a couple of components. Why is this? So I apologize for those that have been in the previous session. These are fundamental components that we need to just learn them, because then the operator will actually leverage them. So we understand when, Steven will talk about pods, what it is. The pod is a Kubernetes concept. It is definition. It is the smallest atomic unit of execution. So you start a pod, you stop a pod, and you can have one or more containers. And it's very much like a small VM, because they use the same namespace, the same network stack. They see each other. You can talk between containers with local hosts and ping the other socket, etc. They are located in a single worker node, so I cannot have stretched pods across nodes. And there's other characteristics. And again, just like we had VM in the past decades, we have containers now. And with Kubernetes, the atomic unit of scheduling is the pod. What does it look like? So let's go down some more technical YAML that we love to hate, but it's there and it works and it's fine. You can use JSON, okay, but then you need to do a little wrapper and talk directly to the Kubernetes server API. But this is, the beginning of working with Kubernetes, usually just the YAML. So we go version 1, and the kind of object I'm defining here is called pod. And just give it a metadata tag. There's a lot of tagging with Kubernetes, which is very, very useful. And you can see the image that I'm leveraging here is an IRIS Community Edition. And I want to expose a couple of sockets that are familiar to all of us running with InterSystems IRIS. So, okay. 1, 2, 1, 2, audio testing. I can do all kinds of things there in the pod. I can define storage, some networking. As you can see here, we're exposing a couple of sockets. So it's very much like Docker Compose. If people have used Docker Compose, pretty cool. Problem is, I have no scaling capability, because it's the basic unit of work, the basic atomic scheduling unit. It's just there. It doesn't do anything. It's also completely stateless. It doesn't know anything about other services, about other kind of objects that I can leverage within the Kubernetes engine. And so it's great for working with it, for learning, for starting off, like when the first Docker run that we did, you start to understand what's happening, but nothing else. So the next more interesting object is the deployment object that we have within Kubernetes. And it's a supervisor scheduler. The YAML that we find here, is more representative of the Docker Compose, if you like, and more similar to that. And again, I declare all my definition here. And one of the main differences with the deployment is I can define the number of replicas. How many of these pods, these containers do you want me to run, basically. I can define the services, what kind of egress and ingress can I do allowed, etc. So we see that it combines a replication controller, it combines lots of other things. And the deployment object is perfect for stateless type of applications. So if I go, a series of web servers that I want to spin up, it's great. So let's have a look at a YAML definition. So as we see, we've got the same API version, the kind is deployment. In this case, we only said 1, but we could have said any integer there. And again, all kind of labels that I can use to group, my replicas if I want to look at them, for example. And again, I'm using a particular, image and mapping some ports. So scaling with deployment is cool because I can see that I can, define a different replica value. But one of the problems with deployments is I have no real knowledge where these deployments object or pods are being deployed. And if one of the pods go down, I have no idea really what's going on. I don't know the IP address. I mean, I can find out all this information, but if Kubernetes starts it up again, it's going to get another IP address. And what about volumes, storage? They're lost. If I ask for a particular storage, then it's very difficult to make sure that I get the same file system that I had mounted previously. So there really are very good deployments for stateless type of work. The stateful set, as we've seen on the previous presentation as well, is really where we are improving, or where Kubernetes improves over the deployment object. So the stateful set object is really the ideal one for stateful, persistent, durable type of workload like we have with a database. And so what we have here is the stability of IP addresses, host name, persistent volumes that we mount. And everything is done in an orderly fashion, in a sequential order. You start the first node, the first pod, and the second one doesn't start until the first one is up and is healthy, etc., etc. So there is this expectation, there's this work pattern with stateful set that says, I know that this server has to be up and running, has to be healthy, then I start the second, then the third one, etc., etc. And this is great, right? If we do, if we create a mirror pairs, if we create shard clusters, it's exactly the type of work pattern that we want. So stateful set example, it's, again, very much, the YAML that we're used to, but the kind of object is a stateful set. I want 3 replica set. And what else do we have here? We have a container 2019.4, and I'm mounting some data, which is cool. And I have a volume claim of type read write once. We said it means only one pod can mount and write to it, which is exactly what we want. If I have an iris.dat file in there, and so. This is pretty cool. The problem comes when I say, okay, so you specify 3 replicas. What are they? Because I want to make sure that the first node is perhaps a primary mirror member, the second node is a backup mirror member, and the third node or the fourth node, maybe some shard nodes or maybe some application servers. We have an architecture, a type of architecture solution that we support with InterSystems IRIS, where we leverage our own protocol, the ECP protocol. We leverage. We also need to run some settings to make sure that you start as primary, you as a backup member, you are the second node of the shard system, the third one, and then so they need to be connected. We need to make sure that they see each other, etc., etc. So the stateful set is very useful. We said that gives me stability of IP host names, persistent volume that I mount. That's great, but Kubernetes doesn't know anything about ECP, right? Doesn't know anything about configuration, doesn't know anything about IRIS. So it's just a platform that allows me to define, an architecture. And so what I find is the stateful set is the ideal job, is the ideal object, the Kubernetes support for our work set, but I still have to do a lot of work. So I don't know what kind of tools, configuration management tools that you use, shell script, etc. But there's the risk that these things become very brittle, and we have to do a lot of work. And we want to make sure that you don't have to do all that work. And this is just a summary of the stateful set to say that we get host name at the top, and by the way, Kubernetes by default it really does exactly that -0 -1 for the host name. It does automatically for us. So whatever the stateful set the host name definition you give it, it just adds that in a serial. Same goes for IP, and the same goes for the persistent volume that we see there. So somebody created a persistent volume, and then there's a persistent volume claim that each pod claims or wants to access and mount, and then there's that host name -0 -1, etc. And so if the node in the middle goes down, then we know the Kubernetes will try to start it up. It will be called again IRIS inst 1 with that particular IP address, .41 with that particular persistent volume claim, DBV IRIS inst 1. Okay, so that's great from the basic infrastructure level, but we still have the issue, right, as we said, of the ECP, the configuration, all those things that are not easy. So that's when there's a reason then to leverage operators. So what are operators? Well, first of all, they were introduced by CoreOS in 2016. Philip Brandon, you might recognize his name. Is on Twitter. It's available. It's always available at Kubernetes. Kubernetes conferences. And the idea was exactly this. He named the operator because he said, "I want to totally replace them, a human operator." And basically, we want the operator to do exactly what a human operator would do. So in our case, configure ECP, configure everything else. And the way an operator works is through what they call custom resource definition. This is part of Kubernetes architecture. It's an open architecture. It's an extendable architecture, and actually goes GA this week with the latest version of Kubernetes 1.16. And so everybody can create operators, Kubernetes operator. They're controllers that controls a particular workload. They're in a loop, and they said, hey, this is the effective state I see in the cluster. You have 5 nodes, but when I look at the declaration, you said you want a 6, so I need to start another one. So they sit there in this reconciliation loop, and they do their job, just like all the controllers. Like we have node controllers, we have pod controllers, etc. Very powerful. So everybody can extend this, and really the bottom line is that it helps the specific, with the specific domain knowledge that everybody has. So in our case, is to make sure that we leverage all the power that we have with ECP, with sharding, with the configuration of InterSystems IRIS. And so the operator patterns are really just a way, then an operator allows me then to package, to define my application, and it just holds specific knowledge that if I use a standard stateful set, I cannot express it with that default YAML definition. I can't say, yes, I want 4 nodes and I want them to be in an ECP cluster together. How do you tell that stateful set? It doesn't understand, right? And so domain-specific knowledge is typically then implemented through custom operators, okay, that allows us to then go and configure, in our case, and do a particular work pattern. So it just does the deployment then of this of the definition, and then their job is really to maintain the application as it was defined and stated in the declaration of the operator. So it can carry out these reconciliation loops that I mentioned, runs upgrade, deals with failure recovery, etc. And so I'm going to hand it over to Stephen, who's going to present to us the details of the InterSystems IRIS Kubernetes operator.
As Luca was saying, you can get pretty far with a stateful set, but where they really fall short is that they don't capture the semantics of your application. They don't know how to talk to your application. They don't know what are the best practices for your application. So And also, there's not really a facility for managing multiple stateful sets. So, you know, pod manages containers, deployments can manage your pods, stateful sets manage deployments with the addition of persistent storage, but there's nothing that really says, that lets you describe the relationship between stateful sets. So here's some examples of application-specific, and I'll talk about them in terms of IRIS, application-specific things that you might want to do that you can't necessarily do with a stateful set. For deployment, configuring your stateful sets to define your sharding configuration, master shard, worker shards, mirroring, who's the primary, who's the backup, where are they located, as Jim was talking about with availability zones, creation of resources, your disks, your persistent disks, creation of load balancers, management of secrets. For example, the demo I give, I've created secrets for the IRIS license key, for my Docker login to get my demo images off of Docker Hub. Also scaling. You know, you just don't want to allow the user to blindly scale up and down your database, because then you're going to lose data. Maybe you want rules, like you can add data shards, but you can't delete them. Whereas application servers, maybe you can scale up and down freely. And management tasks, like backup, for example. How do you tell Kubernetes that you want to do upgrade it should upgrade all of the backup members first, and then if that succeeds, and only if that succeeds, go ahead and upgrade the primaries? How does Kubernetes even know what's the concept of a primary or backup? Whatever state they're in when you created the cluster is not going to be the state, 10 minutes or a day or a year later. So these are all the kinds of things we want to incorporate into our operator. Now there's some things you can do with a stateful set that is very difficult. Here's the smallest example I could come up with of trying to define a stateful set for a mirrored IRIS deployment, where I'm trying to convey that if there's more than one availability zone, the primary backup should be in different availability zones. And this is very lengthy, and trying to capture this for a whole cluster, you'll end up with pages and pages of this stuff. So another thing we can do when you create a custom resource definition, when you extend Kubernetes by adding a new type, is that you can instead encapsulate all of this knowledge and just completely hide it. There's more stateful set stuff was required for that example. Okay. So that's something that's difficult to do with a stateful set. Things that are pretty much impossible to do with a stateful set are to specify a maximum or minimum number of replicas, to prevent, as I was saying, scale in and out of certain types of nodes, to impose ordering on how things start up and shut down, to add application hooks. For example, in IRIS, when you delete an application server, you need to go tell the data master that is no longer available. And Kubernetes doesn't give you a hook to go make a call into object script. Coordinating updates and backups and working with multiple stateful sets. So we have created a Kubernetes operator called IRIS cluster. This introduces a new Kubernetes native type. There's pods, deployments, stateful sets. Now there's a type called IRIS cluster. It adds attributes for configuring sharding, mirroring, availability zones, managing your IRIS key, IRIS password, setting that safely. It makes use of our new configuration state file utility, which allows you to define snippets of your IRIS CPF file, formerly known as cache CPF, to apply to certain nodes. And it knows how to do updates. So this can take a while. So what I'll do is I will start the deployment, give me 5 minutes, and then while it's deploying, I'll come back and give a tour of this new custom resource definition. Get back to my Google shell here. I made the text down here larger. I don't know if you can read the text up here. So the first step to using an operator is the only thing you have to ship is an installer, a snippet of installer YAML. And that YAML basically gives the name of the new type and the location of the container that contains the operator code and its interfaces. So the first step is we're going to run that YAML right now. So kubectl apply-f iris operator installer YAML. I have a different window here. I'll do a kubectl get pods. Okay, and you can see that the operator is now running here. And the next thing I'm going to do is I'm going to run this deployment I've defined here, which I'll give a tour of in a moment. Let's get it started. So, kubectl apply-f iris gs 2019 YAML. In this other window, I'll say watch kubectl get pods. You can see it start to get created. So while it's doing that, I'll lower this. Is it possible to read this text? I didn't see how to enlarge it in here.
Back, yeah.
Okay. Well, I'll highlight things as I go. So here's the new kind, iris cluster. Some of the fields we've added, and I won't show the creation of these secrets. It's kind of boring, but I can show you offline. There's a place for an iris key secret where you can give your iris license. There's a place for your iris CPF definitions for things you want to override in the iris CPF that comes with the iris kit and the iris container. This is a cryptographic hash of your desired iris passwords. This sets the password. This itself cannot be used as a password, and it's completely safe to have exposed and be found and passed around. And we provide a utility, also in the form of a container, for generating these. And we, after some research, we decided this was a little safer than using a Kubernetes secret to manage that. And then we get to the main part of this definition, which is the topology itself. Now, most of these sections are optional, but I've included them, a lot of them here for demonstration purposes. I've defined an arbiter. Okay. I've given the location of the arbiter container. I've given the zone I want it to run in. I should say, before this demo, I created a cluster on Google with 9 nodes spread across 3 availability zones, B, C, and D, in US East. There's 3 in each. And I've given it the Docker Hub secret I created, which allows it to pull this container from our private registry. Here's the data definition. I've said 2, this is a new field. We've added shards 2. Actually, let me go back. There's something I forgot to. Back here, when I was showing that extremely long stateful set definition, something else I wanted to point out is that it says replicas 2. And what does that even mean in the context of an iris sharded mirrored cluster? Did that mean 2 instances and 1 mirror? Did it mean 2 mirrors and 4 instances? It's not a really good mapping between the semantics of iris and the default way of counting pods here. So in place of that, we now have this very simple shards 2. If it's non-mirrored, that's going to be 2 instances. If it is mirrored, it's going to be 4. And here's how you control whether or not this is going to be a mirrored deployment. Mirrored true, location of this iris container. And I've replaced all of that horrible YAML that you saw before with preferred zones. And this is basically saying I want the mirrors, the primaries and backups to be in B and C. I don't want the whole pair in B or the whole pair in C. Update strategy, rolling update. And for the purposes of this demo, 2 gigabytes is sufficient. And I wanted to use this SSD storage class definition that I also created before the demo. And finally, so we saw the arbiter section, the data section, and here's the compute section. These are compute nodes are basically application servers. I want 2 of those, and here the terminology is replicas because these can't be mirrored, so that will actually be 2 of them. And I also want a load balancer put on these nodes. So let's go back to the, let me expand this, and let's see how it's doing here. Okay, and it's created everything. So here's the arbiter, okay, and it's created 1 out of 1 of those. The compute nodes, 0 and 1, there's 2 of those. The data nodes, we wanted 2 shards, and the terminology we chose for this is, data 0 is the first shard, data 1 is the second shard. And because it's mirrored, there's a data 0, 0, and a data 0, 1. The second shard, there's data 1, 0, and data 1, 1. We could look at it differently. If I said kube control get stateful sets, then you see it sort of differently. Now you see the shard, and you can see that shard 0 has 2 out of 2 already. Okay? And even higher level, I could say kube control get my iris clusters, because now this is a new, again, native type, so kube control understands it and can display this. And here's an even more compact definition. Right? I named the cluster iris GS 2019. It's got 2 data nodes, 2 data shards, I should say, 2 compute nodes, it's mirrored, and it's running. And we have time to play some games with the cluster. All right, so first I'll demonstrate. Yeah, I can ask. I can take questions first.
I have several questions, actually. One, a pod, as I understand, is a group of containers, but the containers in that pod, they all have to be identical, correct?
No.
You can't mix them. You can't put like a database container in there and an application server container, because you're going to basically tell the system, in this pod, I want 6 of those containers. Maybe that's how many I've designated for replicas. So how are you going to do that if you're mixing and matching different containers in there?
So
that's the question first
okay.
off.
All right, so let me answer that first. So actually, you can mix and match different containers within a pod, and you should. For example, you might want to put a backup or monitoring container adjacent to the iris container in a pod. Second of all, I've put anti-affinity rules in here to restrict iris to 1 instance per pod, and 1 pod per physical node. But yeah, you can have different types of, and people often do. In fact, you can't have 2 iris containers in a pod, but you can have an iris container and any number of other types of containers in a pod.
Oh, so only 1 container of each type?
You can have as many as you want of each. This operator restricts iris to 1 iris container per pod.
Okay. What is a shard?
A shard is a way we've split up the iris database across multiple nodes.
So replication or?
Not replicated. Simply just divided up.
Okay, so distributed across multiple.
Right. So you do an insert into a table, you've got 10 rows, you have 5 shards, the odds are you'll get about two rows per
it's
shard.
It's an InterSystems IRIS terminology that means that we can horizontally scale your data on multiple nodes.
Your preferred zones. Can you spread the cluster across multiple zones? In other words, let's talk about, like if you're looking at a DR scenario, this takes the place of a DR scenario then, because zone 1 might be a 1 data center, zone 2 might be a completely different data center. So if data center 1 goes down, it automatically fails over to data center 2. So this would then take the place of a disaster recovery scenario or need, correct?
Yeah, so the systems mirroring allows you to define a primary and a backup node. They come in pair, configured in pair, and usually in order to avoid a single availability zone, single point of failure, you make sure that the second node is provisioned in a different availability zone. So it's just HA within, taking care of the 2 availability zone are different.
With a sort of geographical redundancy, though.
Yes,
Yes,
you could lose
That's what mirror does.
all of zone
Well,
B.
mirroring typically is within the same data center. Usually on the old mirrors, you'll have an active actor or an active.
No, we're mirroring across the data centers.
We're mirroring across, yeah.
Across
Yeah.
data centers.
Yeah.
That's what I wanted to know.
Yeah.
That's okay.
So let's try to, try to get pods. So I'm going to open up an IRIS session to node data 0, 0. So the primary, or what started out as the primary in the first shard. I'm going to run IRIS session here. I'm going to set some global. Welcome to Global Summit 2019. Get out of there. now I'm going to delete this container entirely. Control, delete, pod, IRIS 2019, data 00. If I go here and we do watch Q control get pods, you'll see that it's terminating. It should come back. I'm being brave here. Okay, so it's creating this container again. It's going to reattach it to the persistent volume that we created for it, and we'll always do that. It says running. Go back into the session. Instance is not running. Well, maybe it's not running yet. Now it's running. And I can cross fingers. So data is still there. Scaling. Really? Well, up here, I'm going to change the compute replicas from 2 to 4. I'm going to reapply. Q control apply -f iris 2019.yaml. Go back to this monitoring one, and you can see that besides compute 0 and compute 1, now there's a compute 2 creating, and soon there'll be a compute 3 creating. Is this until the end of our total?
Yeah, that's correct. Yeah,
Okay.
correct, yeah.
Okay, so that's done. To show an example of upgrade, rolling update can take a while for it to coordinate everything, so I'm going to do a much simpler update. I'm going to go to the arbiter image. I'm going to change this from this tag from 137 to 139, right?
Yeah.
139. And once again, I will do an apply. Go back here, and we should see that I should have waited for the other thing to finish. I thought it was done. Let's see if it picks that up. I'm not sure what the semantics are for how it locks the changes to prevent conflicts. I'm going to do this again. Unchanged. All right, so I'm going to go change it.
Did you save the YAML?
It saves automatically. So things configured. Okay, so now the arbiter is being cycled. Of course, it's going to come back up with the same version and say, you didn't upgrade, why did you do this to me? But if it had picked it, it should be pretty quick, actually. I can go back and change that as soon as it's done. And then if we do a kube control describe on that, it's running. So now I'm going to do another apply. I'll terminate again. Now when it's done, I'll do a before, and then we'll do an after. Kube control describe pod. There's a lot of stuff here, but there's a syntax I could use to just get that one thing out of it. But you can see that it believes the image is this 137 tag. And as soon as this is back up and running, when I do that again, you'll see it's upgraded to the 139. Creating. Okay. Now you can see that the image has been upgraded to 139. That's about as much as I feel.
Yeah.
That's about as brave as I want to be during a.
Yeah, so this is live on
Live
a
demo here.
GKE Kubernetes cluster. So it's all running there, yeah. Any question?
You have one more question.
Sure.
On your different zones, how geographically different can they be? Right now you have East A and B, or East B and C. What if I wanted to do like an East and then say a Central?
We don't have cross-region yet,
Oh, okay.
or even multi-provider,
Okay.
which we have some of our other products.
provider or multi-region blend?
I'm sorry?
Is this blend multi-region or multi-provider setup with?
This is Google.
No, is the multi-region and multi-provider planned?
Yes. Eventually.
By the end of October,
Yeah,
right?
we have multi-region, multi-provider with our native orchestrator, ICM,
Yeah.
and all those capabilities are going to end up being implemented in the operator as well. Question back there?
So you were saying that this IRIS CPF contains, I guess, all of the different configurations for all of these different nodes. Is that how that works?
Yeah, so for example, a very small snippet, but for the data node, I created this little snippet of CPF where I changed the default globals to be a 16 here, and I changed the system mode to be data. Oh, I forgot a whole part of the demo. This is what I want to do. I didn't, kubectl get services. I'm going to take this IP address, which is the external IP I've put on the cluster. This will help answer your question. Notice I made the system mode be data. I'm going to go to the management portal of that node we created, log in with that password I set, and when I go to system operation, mirror monitor, you can see that all those nodes we created are attached. The load balancer happened to put us on data 1-1. You can see it's attached. The backup is 1-0. Controlled by the arbiter, they're attached to that other node that was created. But you'll notice the system mode is data. Okay, that's just a free-form string that the IRIS lets you put in for system mode. Some of them are special. I think if it's test, it's bright red. If it's prod, it's green, something like that. And then for the compute nodes, I overrode different values here. You could replace your entire IRIS CPF file here. I just wanted to show that it does the deltas correctly. And if I brought up one of the compute nodes, management portal, which I currently have blocked off from the web, you'd see that it would say system mode is compute.
So in that, how did it know to make, so you have two mirrors, I guess? Is that what you have?
Yep, two mirror pairs.
So how did it know that, and how did it know to, because there's only just compute, right? I only see compute, and I see data, and I don't really see where it says do two of those. Or
Yeah, so I created the secret. This is kind of a offline discussion, I think, but I'll give you a hint here. Here's how I created the IRIS CPF configuration map. So kubectl create config map, iris-cpf, which you can see is referenced here as the IRIS CPF. And I said from file data CPF and from file compute CPF.
Oh.
And these are not random names. This data, word data needs to match the name of this part of the topology, and word compute is going to match this part of the topology. And then where these go is, if I go back to if I log on to one of these IRIS instances, I can show you where it landed. If I run bash, okay, so now I'm in an IRIS node. I can go to CD, so I can say IRIS QList. You can see IRIS is up and running. If you look at the data that's been mounted, there's a tempfs in-memory volume called this IRIS sys key with my key, and there is CPF. And in this CPF directory, you can see there's that data CPF file, which exactly contains the contents of that secret that we created before, plus some fields that the operator added that you never saw for doing the shard configuration, mirror configuration, location of the arbiter, increasing the ECP count, and things like that.
Yeah. So I wanted to answer that question also because there was something else in there. So Because we create our own operator, we can express the semantics of what we want. So for example, the mirror pairs, they were simply created because there was mirror colon true, right? You just get that Boolean value. And we know exactly what to do because within InterSystems, our domain knowledge is, okay, if you tell me you got mirror, it means you're going to connect these two together, right? There's a primary, there's a backup. And only the data servers can have that. Application servers or compute nodes, as we call them as well, they're not configured typically in a mirror fashion. The other thing that Steve was talking to you about was that there's a delta of the CPF. That's a new feature that's coming out 2019.4. So if you get the next containers coming out, the next release, you'll be able to play with that. It's a very powerful feature. And we'll be presenting it in the cloud roadmap in the next section. But basically allows you to inject new configuration parameters before an instance runs. Yeah.
I got those in 2019.3, the Delta capability.
Right.
I
Okay.
got in some trouble. Okay, well.
When can we have it?
When you it's done. You just need this operator installer YAML. I'm not going to show that on the screen in case somebody snapshots it.
Do you want to put up the last slide? The last slide?
Oh, are there more slides?
So thank you. Thank you very much for coming to this session, guys. Remember, there's a lot more in terms of containers, cloud, the cloud roadmap. So turn up, and this slide represents some of this interesting session. Thank you.